In the last few videos, we developed the geometric interpretation of the determinant. So we saw that the determinant measures how a matrix transformation scales area, and we also saw how determinants behave under matrix multiplication. In this video, we're going to be looking at one of the most important connections, actually in all of linear algebra, I'd say, namely the connection between determinants and invertibility. This is something we have already seen when we were talking about invertibility and inverses of matrices. It's actually where we first sort of defined this idea of the determinant, at least for a 2 by 2 matrix, but we're going to generalize all that here and discover the fact that a square matrix is invertible precisely when its determinant is non-zero. And this is going to give us a really powerful way to determine whether a matrix has an inverse without actually having to compute that inverse first. And knowing whether a matrix has an inverse connects to a lot of other concepts we've already seen in this class. So there's going to be sort of geometric connections we can make with that matrix if we think of it as a transformation. There's connections to the linear dependence or independence of the columns of that matrix. Just sort of the definition of being invertible, right? So there's connections to being able to row reduce to the identity and being able to solve systems that have that matrix as a coefficient matrix. Connections to spanning sets for the vectors that make up the columns of the matrix. So this determinant, being able to tell whether it's zero or not, and therefore discover whether our matrix is invertible or not, is going to be this really, really powerful tool. And there's going to be even more, applications of this as we move into future sections. So let's start with this example here. Consider the matrix 1, 2, 2, 4. So this matrix takes E1 to the vector, 1, 2. So this vector here, and then E2 to the vector 2, 4. Right, so this vector here, and so the unit square ends up being transformed just to this line, and the area of this line in 2 dimensions is just going to be 0. It's sort of this one-dimensional object, just a line in 2 dimensions. It has an area of 0, and we could see that the determinant of this matrix is 4 minus 4, AD minus BC, and so that's also equal to 0. And the other things we can sort of see here, if we were to try and row reduce this to the identity, we would be unable to do it, and therefore A is not invertible. So just sort of making a bunch of connections right here with this particular example. The other thing we can see is that if we call these columns V1, V2, let's say, we could see that V2 is just twice V1, and therefore this set V1, V2 is linearly dependent, since we can write one of the vectors as a linear combination of the other vector or vectors in general. We can also see that if we were to kind of play around with this, and we can see in the picture, hopefully, that the span of this set is just a line, so therefore it is not all of R2. So knowing that the determinant of a matrix is 0 tells us all sorts of things. And again, there's also more connections that we've already seen with systems of equations and more to come in future sections. There's going to be connections between the determinant being 0 and sort of playing around with null spaces and eigenvalues and other things in future sections. So really, really important thing here. Let's take a look at a 3 by 3 example. So this example here, we've got the matrix A. And so if we were to compute the determinant of this matrix, we would actually find that it is equal to 0 as well. We could see actually the columns of that matrix shown in this picture below, and we would be able to find and show, and you're seeing in the image here, that these columns span a plane in R3. And so if we think about the parallelepiped formed by those vectors that make up these whose columns, thinking of the columns as vectors and the parallelepiped formed by those vectors, then the volume of that would be sort of the volume of this plane of or a part of this plane, a two-dimensional object, and the volume of a two-dimensional object is just going to equal 0. And so, the determinant of this matrix, if we're thinking geometrically, is equal to 0. We haven't actually shown yet how to compute the determinant of a 3 by 3 matrix. That's something we'll get at in this video, but it would equal 0, and we're going to see that later on. And the geometric kind of idea here, seeing that the parallelepiped would be sort of this 2D, this flat object would have a volume of 0. We can also see if we call the columns v1, v2, v3, we could see that v3 is equal to just v1 plus v2. So again, this set v1, v2, v3 is linearly dependent. And we also have the fact that therefore A is not invertible, and the span of this set v1, v2, v3 is not all of R3. So again, the determinant equaling 0 has that geometric idea with the volume of the parallelepiped formed by the columns of the vectors that make up the columns of that matrix, but also these other connections to invertibility and linear dependence of those vectors and the spanning set of those vectors. So all sorts of connections we're making. So the big takeaway, the big idea here, and we're going to explore this further, but wanted to put it up front, is proposition 3.4.10, namely that the matrix A is invertible if and only if its determinant is non-zero. So we're going to explore this a bit further and also introduce a nice way to actually compute determinants of n by n matrices. So matrices may be bigger than 2 by 2. And so just as a reminder, A is invertible if and only if it is row equivalent to the identity matrix. So there needs to be a set of elementary row operations that allows us to go from A to the identity. What we're going to do is explore how determinants change when we perform row operations, which gives us an effective method for computing determinants, but also will give us a way to better understand why that proposition is true, this proposition here, that a matrix is invertible if and only if its determinant is non-zero. So let's go through each of our elementary row operations. We'll start with scaling. Remember, in a previous video, we talked about how we can view each of our elementary row operations as kind of multiplying a matrix by an appropriate, what we call elementary matrix. So, this matrix E here is found by scaling the second row of the identity, the 3 by 3 identity matrix, by K. And so if we wanted to obtain, let's say we want to obtain this matrix B by multiplying the second row of another matrix A by K, so scaling A by K, then that can be viewed as matrix multiplication of A by E. And so, B is equal to E times A. B would be found by applying that elementary row operation to A. Since E is diagonal, we saw in a previous video that the determinant of a triangular and therefore diagonal matrix is found by just multiplying the elements down the diagonal. We'd have that the determinant of E is just 1 times K times 1, which is just K. So the determinant of E is equal to K. And we also saw that the determinant of a product is equal to the product of the determinant. So the determinant of EA is just the determinant of E times the determinant of A. And so the determinant of E is K. So the determinant of EA is just K times the determinant of A. And so the determinant of B is K times the determinant of A. So this tells us sort of how to, what happens when we apply the scaling elementary row operation to a matrix, what happens to its determinant. We sort of effectively scale that determinant as well. Interchanging two rows, we saw in a previous video that what happens to the determinant when we interchange two rows. If we interchange two rows of a matrix, then the determinant is going to, so the determinant of interchanging two rows of the identity gives us just -1. And so the determinant of the matrix B, which is a result of interchanging two rows of a matrix A, which can be thought of as this matrix multiplication again, right? So B is PA, then the determinant of B is the determinant of PA, which is the determinant of P times the determinant of A, which is -1 times the determinant of A. Okay, so that leads to this formula down here that the determinant of B is negative the determinant of A. And then last one, row replacement. So if we take the identity and add k times the first row to the third row, then we get this example matrix E here. So if B is E times A, then B would be obtained by multiplying by adding k times the first row of A to the third row. So applying that elementary row operation. E is triangular here, and so again, the determinant is just going to be the product of the elements on the diagonal, which are all 1. So therefore, the determinant of E is 1, and therefore the determinant of B is just 1 times the determinant of A, or just the determinant of A. So it turns out that this elementary row operation of replacement has no effect on the determinant, which is pretty interesting. So summarizing and putting all these together, if A prime is obtained from A by scaling a row by K, then the determinant of A prime is K times the determinant of A. And actually, oftentimes when we're doing this, we care more about what happens, we ultimately want to compute the determinant of A. So I might want to actually write this in the other way, that the determinant of A is equal to 1 over K times the determinant of A prime. Which is equivalent to that, but might be more useful. Same thing down here. The determinant, if A prime is obtained from A by interchanging two rows, and the determinant of A prime is negative the determinant of A, I might just want to view this as the determinant of A is therefore negative the determinant of A prime, and then the row replacement does not change the determinant. So let's so how is this going to be useful? Let's see how this plays out. If we are going through our Gaussian elimination to A, so our elimination method, applying that to a matrix A, and we get that to an upper triangular matrix U, then those row operations will tell us how the determinant of A and the determinant of U are related. Right? This proposition will sort of tell us how each row operation is going to affect that determinant. And then once we have this upper triangular matrix, we can find its determinant by just multiplying the elements down the diagonal, right? So U11, U2, U2, U through UNN, these are just the diagonal entries of U. So let's see an example here. So we'll start by looking for this determinant. We want to row reduce this to an upper triangular matrix. So the determinant of 2, 1, 1, 1, 1.5, -1, 1, 2, -3. So we might start by interchanging two rows just to get a 1 in that position there. Interchanging two rows of a matrix is going to lead to the determinant being the negative of the other determinant. So this is negative the determinant of 1, 1.5, -1, 2, 1, 1, and 2, -3. And then let's do some row replacement. So we'll do row 2 minus 2, row 1, row 3 minus row 1. This is not going to affect the determinant, so we still have that negative sign from the interchange. So that'll be negative the determinant of 1, 1.5, -1, and then 2 minus 2 is 0. This is going to be 1 minus 3, so that's a -2, and then 1 minus 2 times -1, so that's 1 plus 2, so that's a 3. And then 1 minus 1 is 0. And then we'll have a 2 minus 1.5, so I guess that's a 0.5. and then a -3 minus 1 times -1, so that's a -2. All right, at this point, maybe we want to scale row 2 by a 1/2. So we might want to do a row 2 divided by -2. Going back to this slide here, so, scaling the resulting matrix will have a determinant equal to k times the original determinant, but we really care about the determinant at A. So if we're dividing by a -2, then we might want to think about, really what that's going to do to the determinant at A, which is going to scale it by 1 over -2, or multiply it by a -2. So really what's going to happen is we'll have -2, and we already had a negative sign here, right? So -2 times a negative will end up to just be 2 times the determinant of whatever we get when we scale that. So 1.5, -1, 0, 1, and then -1.5, and then 0.5, -2. And then one more step, let's get a 0 here to get this to be upper triangular. So we'll do row 3 minus 0.5 row 2. So this goes to 2 times the determinant of 1, 1.5, -1, 0, 1, -1.5, and then 0, 0, and then that'll be a -2 minus 0.5 times -1.5. So I guess it's a -2 plus a 0.75. So that should be a -1.25. Okay, so this result here is now upper triangular. So its determinant, so we have this 2, right? This is that 2 there. And then the determinant of this matrix here is just going to be 1 times 1 times -1.25. And so the final answer here is 2 times -1.25, which is -2.5. Okay, so the determinant of that original matrix is just -2.5. Now, another way you could do this is sort of go through your row reductions and then try and retrace your steps and kind of apply this proposition in each step that you would require it. So each interchange, make sure you have a negative, and each scaling, make sure you scale the determinant appropriately. But my sort of preference is doing it this way, sort of figuring out how the determinant is affected as you go. It's a little more work as you're sort of row reducing, but once you get to the end, you don't have to do any of that retracing, which is sort of nice. The really the most complicated interaction here is the scaling. And so, one thing you can think about, and what helps me is that when you scale a row, what effectively happens to the determinant is what I think of as kind of a factoring. So we scaled this row here by a -2, and you can kind of think about that -2 being factored out of the determinant, if that makes any sense. So we had this -2 kind of coming out front, and so -2 times -1 turned this into a 2, and then this -2 factored by a -2 became a 1, and this 3 factored by a -2, so divided by -2 became a -1.5. So I don't know if that helps. That's sort of a helpful way for me to think about it. The row replacements don't change the determinant at all, so nothing to think about there. And the interchanges just introduce a minus sign, so that's not too tricky. So it's really just these scaling. So that helps me with the scalings. But in any case, the result here is -2.5. So this particular matrix is invertible, right? Its determinant is non-zero. Just to reiterate that, so we know U is invertible if and only if all its diagonal entries are non-zero, and since the determinant of U is just the product of the diagonal entries, then it follows that U is invertible if and only if its determinant is non-zero. Okay, so a little bit easier to recognize when a triangular matrix, right? If we have a sort of triangular matrix, U11, U22, down to UNN, all zeros here, sort of whatever we want up here, This is going to be invertible exactly when all of these diagonal entries are non-zero. If one of them is zero, right, then we immediately know that this will not be able to row reduce to the identity, and if they're all non-zero, then we also hopefully can pretty quickly tell that this can be reduced to the identity, so therefore is invertible, and so the determinant would be non-zero. And then connecting that back to A and proposition 3.4.10, the determinant of A is non-zero. If the determinant of A is non-zero, then the row operations used to obtain U only multiply the determinant by non-zero numbers. Therefore, the determinant of U is non-zero, which implies U is invertible, and hence A is invertible. So A is invertible implies the determinant of A is non-zero. And then looking at the determinant of an inverse. So if A is invertible, then A times A inverse is the identity. If we take determinants of both sides, right, the determinant of A times A inverse, so that would be the determinant of A inverse, which is just the determinant of A times the determinant of A inverse. Okay, so that gets us down here, and that equals the determinant of I. The determinant of the identity is 1. So solving this, we have that the determinant of A inverse is 1 over the determinant of A. So that's proposition 3.4.12. If A is invertible, then the determinant of A inverse is 1 over the determinant of A. And it's a good thing that this is only going to happen when the determinant of A is non-zero, because, we obviously can't divide by 0. So this is another reminder that the determinant of A being non-zero is sort of imperative for A having an inverse, so A inverse even existing. And this is a nice connection to what the value of the determinant of that inverse is.